Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is RT 120, Hydraulics. Today we're going to have a discussion about flow control methods. And before we do so, let's start off with this very simple topic here. A double-acting cylinder extending and retracting. Okay, so here is our cutaway view of our double-acting cylinder. Obviously we've got our cap end, our rod end, got our inlet ports, we've got our piston face and our rod. And my question to you, does the speed on extension, does it depend upon the flow rate entering the cap end, or does it depend upon the flow rate leaving the rod end? And the answer is both. Okay, let's flip this thing around. Does the speed on retraction depend on how fast the rod end is filled, or does it depend upon the speed at which the cap end is drained? The answer is, again, both. Both will influence the speed at which this cylinder is retracting. Okay? So we've hit upon two key means of controlling actuator speed. Basically, meter in is controlling flow into an actuator. Meter out, appropriately enough, controls flow out of an actuator. And there's a third method, which you may or may not see, called bypass, sometimes also called bleed off. And I'll hit this one later on. This is kind of a different way of doing that. So remind me, I'm gonna hit this one later. But let's talk about meter in and meter out. And you're going to hear these things a lot because this is how cylinder speeds and actuator speeds are controlled, meter in and meter out. Okay, let's just talk again as the, let's stick with the retraction since that I've drawn. That's what I've got up there right now, retraction. Okay, meter in versus meter out. I could control the amount of flow coming into it. Let's say I limit that to 4 gallons per minute. Well, again, this space is going to fill up at a rate of 4 gallons per minute. I've controlled the retraction speed. Now, what happens here? Meter out. Let's say I meter out this thing, and let's say my inflow is as fast as it possibly could be. Whatever the pump can supply, I can do that. But let's say I limit this draining to, let's say, 2 gallons per minute. Can it extend any faster than draining the space at 2 gallons per minute? Well, the answer is no, because there's fluid in there. You know, and again, fluid is an incompressible, for all intents and purposes, an incompressible medium, regardless of how fast it's coming in. Basically, there is fluid inside that cap end that's pushing back, and it's draining at a rate of 2 gallons per minute. And it's going to retract at a speed based on a meter out scheme. Okay, so meter in versus meter out. Let's take meter in first. Okay, again, meter in, controlling flow into an actuator. Schematically, what's it look like? Okay, let's say I want to have meter in extension. Where do I control the flow? So meter in extension. So meter in extension implies that I have to control flow into this actuator, in this particular case, this double acting cylinder, that will extend it. Which one extends it? Well, pretty obviously, flow into the cap end will extend this guy. I have to draw that again. That's horrible. So if I put a flow control valve here and it's got a check valve bypass in that orientation, that is meter in extension. So what's going to happen, I've controlled my cylinder extension rate by whatever fluid flow that my pump can possibly produce is coming in this direction. Tries to go through the check valve, it can't. It's forced to go through the flow control valve, which creates a pressure differential, and excess flow is going to be dumped over the pressure relief valve. And what happens here is basically, let's say it's 2 gallons per minute. Let's say we've set it up here. This thing will extend at a speed limited to our flow rate of 2 gallons per minute. Okay, so let's say this volume here happens to be 1 gallon. How long will it take that thing to extend? 30 seconds. So that is a meter in extension. Okay, what happens if I want to retract this thing? Well, I would put pressurized flow at the rod end now. Unpressurized flow comes in here. It tries to go through the flow control valve and it tries to go through the check valve, which basically it's going to push that valve off. See, it's going to just flow as fast as it possibly can out of that cap end, and basically it's going to retract at whatever speed that pump can provide. So meter in extension, and if I've hooked up my flow control valve in this manner here, it's going to control the speed at which it extends, but it's going to retract as fast as it possibly can. Okay? All right. And I'm doing this pretty slow. So let's take this the next step. Meter in retraction. Where do I put my flow control valve? And if it's got a check valve bypass, how do I set up the check valve bypass? Okay, meter in retraction. So to get this double acting cylinder to retract, I need to put pressurized flow on the rod end. Okay? And that is the orientation, the correct orientation of that flow control valve. Okay, so pressurized flow at whatever flow rate the pump can possibly provide has to go through here and tries to get through the check valve. Nope, can't do that. So it's forced to go through here at a flow rate, let's say again, 2 gallons per minute. This has a volume of half a gallon. How long does it take to retract? 15 seconds or a quarter of a minute. Okay, so we have controlled the speed at which it retracts. Let's say we want it to retract slower. Change that flow rate to 1 gallon per minute. By adjusting their needle, it takes 30 seconds for that to retract. We are controlling the flow into the actuator. Okay, so that is meter in extension and retraction. Meter in extension, got a flow control valve on our cap end, oriented in the following manner. Look at that check valve. Meter in retraction, we have a flow control valve on our rod end, and our check valve is oriented in the following fashion. Okay, let's talk about something about meter in before we move on to meter out. This is all well and good. This is a great means of controlling a cylinder's extension and retraction. For push and pull loads. When I say push and pull loads, I'm pulling it this way, pushing it that way on something. This is not a really good way of controlling the flow rate, lifting and dropping an object. And there's a reason why. Let's say here's an incredibly high weight, large weight there. And let's say I'm going to have meter in extension. So meter in extension, I'm controlling the speed at which, because flow can't go this way, I'm controlling the speed at which the cap end fills. And I can control the speed of the ascent. What happens when I want to descend this object? Basically, this becomes hooked to the tank now, low pressure flow. Low pressure flow, it's going to push that check valve off the seat, basically meaning that whatever flow rate produced by this, it can just go ahead and flow through that flow control valve backwards because it's got a check valve bypass in it. What's the problem here is basically this load is sitting on this cap end pool of fluid with no pressure in it, and it's just going to slam to the ground. And you sure as heck hope that you are not underneath that thing. So you're like, aha, I've got an idea. Let's fix this and put a meter in retraction on this thing. So you can do both. You can do both. So that way I'm going to control the amount of fluid going in to the rod end. So that way I'm controlling, because Jim just told me right here, meter in retraction. I'm going to set it up this way. So meter in retraction, pressurized fluid flow, can't get through the check valve. So I'm controlling the rate at which this rod end is filled. And I should, in theory, be able to control the speed at which that thing retracts, thereby controlling the speed at which it descends. That answer is totalmente falso. You would expect in a push and pull system, yeah, that's totally fine. Go ahead and do it, by all means. Do a meter in retraction on that. It's not going to work in this lifted object case, because here's what's going to happen. I'm going to draw this again. I know you're controlling the flow rate that's entering this rod end. And I know that you're controlling the extension of this thing this way. But like I said before, this is low pressurized fluid. It's not going to, it's going to push that ball off its seat. It can't support that incredibly large weight. So basically what's going to happen is that piston face is going to slam to the ground because that fluid drains out of the cap end extremely fast. And it's going to go so fast, it's going to leave that fluid right there behind as that drops into there. I know you're controlling the rate of fluid going into there, but that doesn't matter, is because that piston face is already slammed to the bottom because that pressurized fluid here has no pressure or very limited pressure and it can't hold it up. What's going to happen here? You've developed a vacuum, and these things are going to enter a atomized or a gaseous state. Basically, this is a cavitation event. Okay? Those things leave the liquid state, enter the gaseous state, and you've got this induced vacuum into the system. And eventually this thing is going to fill up. And you may, depending on the pressure of that thing, you may have a cavitation event where those gaseous particles there implode. But the fact of the matter remains that weight just hit the floor really hard, and you might be underneath it. So a meter in, extension and retraction. And here what I've done is both. I've got a meter in, retraction. Here I've got a meter in, extension. It's really only good for push and pull loads. If you've got a suspended weight or if you've got an overrunning weight, consider the following here. Here's a good application. Here's a push and pull load. Again, this is a good use of meter in. Here is my meter in extension. I'm controlling the rate at which I'm extending it by controlling the amount of fluid entering the cap end. Here is my meter in retraction. I'm controlling the amount of fluid which enters the rod end. I'm controlling the speed of filling that rod end. Here's a bad application in a push and pull. What would happen if this was, I'm drawing this thing comically long here, kind of a teeter-totter application? Basically here's a weight, and if I push it, it's basically supported on this thing, and here's a kind of where it's attached, and here's this rod. All is well and good until it gets to this point right here. So that's good as long as we keep it within that. That's good push and pull. Well, it's good push. But now what happens once we break this plane right here? It becomes an overrunning load. Overrunning. So even though I have a meter in relationship, can't go that way, has to go through the flow control valve. I control the flow rate at which I'm filling up the cap end. So I'm meter in extending, and I'm controlling the rate at which that weight reaches the 0-degree axis here, straight up and down. What happens once I break this plane right here? It becomes overrunning. My weight wants to fall away. It's very similar to this circumstance right here. Okay, so what happens is basically now, to redraw this thing, it's falling as fast as possible, and I know I'm controlling the rate at which I'm filling this space. It doesn't matter because there's no pressurized flow. There's no pressurized fluid right there. That's draining as fast as possible. We've got another cavitation event where that liquid can enter the gaseous state. Okay, it's basically separating the piston face from our cap fluid there. So that's an overrunning load. So an overrunning or a suspended object, meter in is not such a good idea. Push and pull, by all means, go ahead and do it. And like I said, you could do both of them. So here's a meter in extension, meter in retraction. If you're that concerned about the rate at which things extend and retract, by all means, put one on the cap end, meter in, put one on the rod end, meter in. Okay, that's for both of them, push and pull. Do not use meter in for suspended loads or overrunning. So how do we control suspended loads and overrunning loads? Well, we already talked about meter in. Pretty obviously the answer is meter out. Okay, so meter out. We already figured out in extension, we can control the flow rate into this thing. That will control the extension speed, but we also mentioned that regardless of the flow into the cap end, if we control the flow rate at which it was leaving the rod end, we could also control the extension. So there's a meter out extension. Where would we put that? Well, pretty obviously on the rod end. We want to control the flow rate leaving the rod end. So all flow has to go through that flow control valve. Okay, so for this the same setup right here. So we are having a meter out extension, regardless of the flow rate capable of entering this end right here. It doesn't matter because we are limiting it. Let's say it's 2 gallons per minute. And this is an area of, a volume of 1 gallon. How long will it take for this thing to extend? Well, if this is a volume of 1 gallon at a flow rate of 2 gallons per minute, it's going to take 30 seconds for that to extend. Okay? So meter out extension, it's on the rod end. Dig it? Versus meter in extension, it was on the cap end. This makes perfect sense too. I mean, here is meter in extension, and there's meter out extension. Just refreshing again. Controlling flow rate into the cap end, that is meter in extension. Here is what we've just been talking about, meter out extension. Okay, so 2 ways of controlling it. What is our advantage here? Well, let's say I've got a suspended load. And it's this moose that I just shot in the face, and I'm going to grind him up into sausage. So I want to lift him. What I do is I put pressurized flow into here, and it retracts the rod. But now I want to gently lower him into my sausage grinder. What's going to happen without any metering scheme here? Basically, I'm going to hook this to low pressure tank flow and that to pressurized flow. And again, just like we saw earlier, the weight of that moose is pulling down on that thing, and it's going to leave the fluid inside the cap end away. It's going to create a cavitation event because this side here can't support the weight of the moose because there is no pressure on it. So we got to go ahead because we don't want to damage our moose there. We're going to go ahead and find a way of slowly lowering him into the sausage grinder. How are we going to do that? A meter out extension. Basically, what I do, I put my flow control valve in this orientation. So now pressurized flow enters here up to the maximum of whatever the pump could provide. But what's draining out of the rod end here can't go through the check valve, it has to go through the flow control valve. And by varying the setting on the flow control valve, I can lower at whatever speed I want to. Pretty neat, huh? Okay. And again, as fast as possible, I want to lift this moose. So we switch our directional control valve. So now this is pressurized flow, pushes the ball off the seat, and I can lift that thing as fast as possible. But again, meter out extension allows me to drop him at an incredibly controlled rate. Okay, so is that the only way? No, let's say we've got it hooked up in this orientation. Again, here's a great weight. How do I avoid that weight from slamming to the ground? Well, I want to do meter out retraction. So meter out retraction, it's on the cap end. And it's hooked in the following fashion. Obviously, flow control valve, make it variable. Make it so the check valve forces the outgoing flow through the flow control valve. Means you have to hook it up in that fashion. So again, I want to slowly descend this weight, outgoing flow from the cap end. Can't go through the check valve, it's forced to go through the flow control valve. Okay. The immediate question that some of you guys are probably, if you're getting this thing so far, meter in and meter out, well, can I do both of them? Yeah, totally, you can do both of them. Watch this. What about this system right here? What is it? Meter in extension, meter in retraction, meter out extension, meter out retraction. There's 4 choices. I'm even going to list them right here. And there's our 4 possible choices. So let's just think about when pressurized fluid flow enters the cap end. So pressurized fluid flow is coming along, forces this valve off the seat. Can't go through that way. So I'm controlling the flow rate into the cap end, which is going to extend the rod. So I'm controlling flow rate into the cap end, which is going to extend the rod. I am a meter in extension mode here. Supplied by which flow control valve? This one. Okay. So there's another flow control valve in there. It's also on the cap end. So that is the answer. That's the first answer, one of 2 correct answers. So now, what happens when pressurized fluid flow enters the rod end? Well, fluid flow from the cap end is going to hit this flow control valve. It's going to bypass it. It's going to hit this flow control valve. It can't bypass it. And it's going to be forced to go through this flow control valve, controlling the flow rate out of this cap end while it's retracting. Meter out retraction. So I've controlled the extension and controlled the retraction by putting flow control valves oriented in the following manner. That's critical. On the cap circuit. If I wanted to, I could put a meter in retraction, meter out extension on there. But again, I mean, that's you're killing yourself there. You're adding more and more components. You're adding more connections, more inefficiencies, and the big one, more money. So think of the easiest way to go ahead and do it. Think of the cheapest way to go ahead and do it. Think of what's critical to the control of your system. You know, a lot of it is, let's say if you're doing a load handling system where you're requiring the speed of approach to be very controlled and slow to an object, go ahead and put in, let's say it's this way, the approach there, go ahead, put in a meter in extension or a meter out extension on there, whichever one. So you're controlling the extension speed. But if you don't care about the retraction, don't put anything on there because, you know, that's just dead time. Just get that thing back as fast as possible. So again, using the correct scheme And using the minimum number of correct schemes is going to save you money on your system. Again, you're going to save yourself some trouble and heartache and connection time there too. Okay, so what's the advantages and disadvantages for meter in? It's pretty obvious that we shouldn't be doing a meter in scheme for suspended or overrunning loads. What's the disadvantage for a meter out? Well, think about what's happening, especially in our moose example here. So I've got pressurized flow entering here, and there's creating a pressure differential across this flow control valve, because that's how flow control valves work. So there is pressure inside here, and basically there's pressure forcing down on that cap end. Here's our cap end. Let's say 800 psi is on that area. Think about this, it's a smaller area, and you got the weight of the moose pulling down on that thing. Think of what's occurring there. It's a smaller area. You've got the pressure from the pressurized flow on that cap end acting upon that thing, and you've got the force of that moose pulling down on a smaller area. This is what's known as a pressure intensification. Very similar to our series circuits there. Not only do you have, and again, this is a suspended load case here. If it was just the pressure, I mean, this is bad enough here. 800 psi, and let's say that is 4 inches on the cap end, and then let's say it was 2 inches on that rod end, that annular area. It's basically going to be double the force. 800. Excuse me. It's going to be double the pressure. Basically, if there's 800 pounds of pressure, pounds per square inch of pressure acting on a 4-inch square area, 3,200 pounds of force acting on that cap area. That same 3,200 pounds is acting on an area of 2 inches. So it's 1,600 psi. Basically, pressure intensification has occurred. So even though my system is providing 800 psi, the simple fact that in that rod annular area is smaller, I could potentially exceed the pressure of the working pressure of my lines. So just be aware that hey, my system's 800 psi, and these hoses are good to go for 1,200 psi, so I'm good to go. Yeah, you might not be because of pressure intensification. And now go ahead, add an additional, let's say, how big's a moose? I don't know. A lot of pounds. Just add more force pulling down there. So you 1,600 psi may become 2,400 psi. You've totally blown that hose there. Okay, so be aware. Meter in has disadvantages in the fact that you shouldn't use it for suspended and overrunning loads. Meter out has disadvantages because pressure intensification can occur, especially in the lifting the dead moose problem. Okay, the last and third method of flow control methods is called bypass, or sometimes you'll call it bleed off. And you may run into these. You may run into a system like this. Bypass and bleed off, whereas meter in and meter out are directly controlling the flow in the lines they're attached to. Bypass is doing something different. And the way I like to think about bypass, this is the KCL of hydraulics. What's the KCL? Kirchhoff's current law of hydraulics. Let's say I've got a cylinder here, and it's hooked up to a directional control valve, which is hooked up to a pump, and pressurized flow is entering this here. What would happen if I just stuck a flow control valve off to the side and returned it straight to the tank? And let's say I set it up for 1 gallon per minute. And let's say my pump was capable of producing 8 gallons per minute. What's my flow rate to my cylinder? Well, quite obviously, 7 gallons per minute. Dig it? So it's the Kirchhoff's current law. Basically, if I know that I got 8 coming in this way, I know I got 1 coming into that way, and I'm talking about this node right here. Basically, sum of what's coming in, minus what's coming out, they should add up to each other. Okay, and now let's say my pump is still at 8 gallons per minute, but I want to slow that actuator down. I want to slow the extension speed of that guy down. What do? Increase the flow rate back to the tank. And what happens is I proportionally decrease the flow rate available to that cylinder. So that's a bypass or a bleed off method. Just a means of purposely diverting flow from an incoming stream. It's an indirect means of control, whereas the meter in and meter out, those are direct means of controlling, by directly controlling the amount of flow into or out of a actuator. Okay, so that is pretty much it for our meter in, meter out, bypass and bleed off schemes. Definitely check this thing out a couple times if you're unsure. Look at a number of examples in the book, ask me questions, and we are going to be working on a lab on this. We're going to go ahead and try to meter in a suspended load. What happens? It's probably going to crash to the ground. Then we're going to try to meter out it. And hopefully that load will descend at a controlled rate. This pretty much concludes flow control methods.